So, in the last class we started about the metal-carbon complexes, and we discussed and we started the discussion about its applications as versatile catalysts for multiple and useful reactions. So, in the last class, if you remember, we started to know about the metal-carbene, what are the metal-carbene complexes and also metal-carbene complexes, and what are the basic chemical structure. And today we will be continuing to our discussion about the metal-carbene, and today with special focus on the types of alkene metathesis reactions, okay, and its catalysts. And today mainly we will learn that how many types of reactions can be performed by the same type of molecules. So, it is basically you will learn here, and you will see that it is a kind of a single law, single key, okay, for multiple locks. Okay, so this is really interesting. See, one catalyst can perform many various types of alkene metathesis reactions. Okay, so that's why it's so popular and useful in various domains of applications, starting from the drug industries to the polymer industries. Okay, so we'll be discussing. So this one now you are familiar. So this is called the alkene metathesis reactions. So here you will see that this one, if you can break it, and then you can then again join the half, okay, half of the alkene, okay, to the another half the alkenes, and you will get the new alkene. So these are the new alkenes, okay, and the basic structure of this kind of catalysts is this one. So that is actually the metal-carbene, okay, and you will see that formally you have double bond. So we can write like this one. There are other ancillary ligands are there, okay. So these are the basic structure of the metal-carbene, and various type of reactions we can perform, okay. As example, like if you see here C1, okay, I'm just writing only the alkene moiety, okay, I am not writing a real molecules here. So C3, C4, so using this kind of catalyst you can get the C1, C3 plus C2, C4, okay. So you will see that two type of new alkenes you are getting, okay, and this is obviously the, so what here basically you see the exchanging of the carbon fragments, okay. So here that's why it's called the cross metathesis reaction, cross metathesis reaction. What you are getting basically, you are here, I'm just showing in a different color so that it is easily. So here basically, so it is breaking here and joining with this one and joining with this one. So you are getting two new alkenes from other two alkenes, okay. Now very similar, you can, if this is, okay, suppose this is a terminal alkene of one longer carbon molecules, okay, or acyclic molecules. So you will see there is some spacer here, okay, that I am not writing in a real molecule, I am just showing the strategic way, okay, how what are the. So this is now if you if you react with any catalyst, here I am catalyst means I am mentioning about the alkene metathesis catalyst, okay. Now what you will be getting? You will be getting again the same like cross metathesis reaction. You will be getting like this one, and C2 C4. Okay. So basically the reaction is same. Okay. So as you see the cross metathesis, so here breaking here, and then adding this one and adding this one. Okay. So this is called the ring closing metathesis reaction. Okay. So basically you are getting a cyclic organic compound from a acyclic organic compound. Okay. So this is the cyclic and this is the acyclic, and this reaction called ring closing metathesis reaction. Okay. So this is the cross metathesis, we call CM. This is called RCM, ring closing metathesis. Okay. And various type of similar reactions can be performed. Another which is very common. Okay. You will see that C, again I am showing as just as a unit, as I told, I am not showing any real molecule. So now I am doing the reverse one. I am taking a cyclic alkene, and then what will happen you will see. Okay. This one, and I am taking another alkene and taking and treating with this kind of alkene metathesis catalyst. So now what will happen? Okay, you can imagine what will happen. So it's basically the reverse reaction, and reverse reaction. So this is C1 C2 and C3 C4. Okay. So that means you will see here that I am making a cyclic to acyclic. So basically here I am closing the ring and here I am opening the ring. So that's why the name is ring opening metathesis, ring opening metathesis reaction. Okay. In short, we call ROM. So these are the three very important we can call the reaction protocols by the alkene metathesis catalysts, and using these three type of reactions you can also do the various type of advanced alkene metathesis reactions. But as I told, basically the reactions pathways are exactly will fall in these three categories. So what are they? And you will, after learning all the possible metathesis reactions, you will understand how versatile applications are possible. Okay, including the polymerization catalyst. Okay, and that's why it's so popular. So let's try to understand in more depth. Okay, and here you will see this is, we already discussed that what are the strategy in the SOP. Okay, SOP means cell higher olefin process. Okay, in the last class also I just mentioned briefly, and you will be realizing here what we are doing. So we are doing basically using a catalyst, and we are making new alkenes. Okay, and here again the new alkenes. Okay, and using the same catalyst. So what you are see basically the changing of the R groups, the substituents on the alkene. Okay, and suppose if with this one, if you make a want to make a higher alkenes, you can start from the lower alkenes, then it will react with a medium alkenes with a medium number of carbon atoms, then it will be higher, and then again that higher number of carbon atoms containing alkenes will react with another alkene, and slowly it will increase the number of carbon atoms in the alkene, and that is the strategy we make alpha olefins from the simple ethylene. Okay, so that is really very interesting, that you will see that how the metathesis catalysts are used in and this is quite an old process. It's not that it's very much kind of a very advanced. Okay, so this is a old process, the soft process, but very useful, and using the concept of the alkene metathesis reaction. So that we already discussed, so I will not go in again to repeat. So very similar, as I told, that cross metathesis reactions. Now you understand. So I already discussed that what is the cross metathesis here. So it's basically, you will see you are breaking the bond here, okay, and here, and you are making, and you are basically threading this R1 and R2, and you are making a new alkene, okay, and you are getting the ethylene, that is this part, okay, this part and this part. So you are making the ethylene. So this is called the cross metathesis reaction. So basically the exchanging of the substituents of one alkene, okay, fine. And this type of reactions, okay, as is called the ring closing metathesis. So it's basically, as discussed just now, that you can make a acyclic to cyclic, okay, and here you will see that this is very common, okay, using the catalyst. I will come in more later in detail about the catalyst structure. I just want to now discuss or give the highlight about the various type of the alkene metathesis reactions. So here one very real example I am giving, like if you have a X, okay, and like this one, okay, and if you use the catalyst, that is the alkene metathesis, here I am catalyst means alkene metathesis catalyst, and X is equal to maybe oxide or maybe amide kind of things, okay, and sorry, this is NMe will be, okay, it may be NR, fine. And then what will happen if you do the ring closing, then what will happen? So this you will get a 5-membered alkene like that, okay, and as a byproduct you will get the ethylene, okay. So this is routinely used in, as discussed, in to make the valuable organic compounds in drug industries, or as in other applications. So this is one of the very popular strategy of making a big cyclic, okay, molecules from a linear molecules using the metathesis reaction strategy, okay, fine. So here you will see that in the ring closing alkene metathesis reactions, there are, if you see, this kind of alkene metathesis reactions goes through a through 2+2 cycloaddition through metallocyclobutane, okay, complex. So I will show how it is possible, okay. So if you now see, if you consider these two steps, okay, for forming for the metathesis reactions, there is two possibilities, okay, and that we will be discussing now. The ring closing metathesis, what are the different pathways are possible? One is the pairwise and one is the non-pairwise, and what are they? Okay, it is easy to understand. Okay, if I here you will see that I'll you can practice with me so that it will be more clear to you. Okay, now I am considering as path A. the possibility number 1. Okay, I am taking a arbitrary molecule and the catalysts. So let's say this is the MCHR. Okay, and this is obviously arbitrary, so just keep it like third bracket. I am not mentioning the real metal center or any and the ancillary ligands. Okay, now I am reacting with one alkene. Okay, so this is my R prime and this is are just simple hydrogen. Okay, now as I told that this goes through a metallocyclobutane intermediate. Okay, so what are these? So this is basically like, okay, CHR and okay. Now then what will happen? You will see here. So this is my R prime. This is the R prime group, that the group on the alkene, and then what will happen? You will see that okay, now we can further, it can now it will be the breaking of the metallocyclobutane. So what alkene will be now formed? The new alkene will be like this one, okay, and that one. Okay, now so you get CHR prime and you will get the CHR, so that is this one. Okay, CHR and CH2. Okay, and another possibility may be there, that is the this one and CH2, that is 2 metallocyclobutane will be may form, that is the this one. Okay, now so is basically this alkene, how it is rearranged, either this way or either this way. Okay, so this is will be favored, and if you get this one, then what new metal alkene you will get? You will get this one, and you will get, so this like this way. So you will get a new alkene and also the cis. Okay, and here obviously the hydrogen and hydrogen will be there. So this is will be the trans and this will be the cis. Okay, now again the MWCH, now this is formed, this one, and now this one can react with MCH2 plus the original alkene, that is the this one. Okay, H, and again it will form the metallocyclobutane, that is the CH2, and okay, so this is the R prime and this is again the CH2. Okay, and now this will, now again it will break to this one and that one. Okay. So, you will get again M double bond CH R prime and you will get the ethylene. Okay. So, this is the another one possibility. So, here what is happening, you will see that this is called the metallocyclobutane with odd number of carbon. So, here odd means 1, 2, 3 number of carbons. And what are the other possibilities? The path B. Okay. So, path B is basically two alkenes will interact simultaneously. So, suppose this is my metal fragment, okay, and I am this is my CH and similarly CH2 RCH. Now, there will be pi interaction. Okay. So, there will be pi interaction here and then it will form like this one. Okay. So, here CH2, CHR, CH2, CHR. So, this kind of intermediate and then eventually you will get the new alkenes. Okay. So, that is the RH okay. And CH2 double bond CH2. Okay. So, is basically what you are getting, we are getting here this kind of, so here and here like that. So, in this case so now try to understand what are the basic difference here. So, here metal in this path A, metal-carbene plus 1 alkene and here the metal-carbene plus 2 alkene. Okay. So, that is why this is called pairwise and this is non-pairwise. So, two type of mechanism are possible and experimentally it is followed. It has been observed that path A is the best possible mechanism. This is also proposed by the scientist Chow Win. Okay. Now, you will now ask that how to prove it. Okay, that how it is happening, non-pairwise, pairwise. Two possibilities are there. One is the pair and one is the non-pairwise. Now, how to prove it? You can set a very simple reactions. Okay, suppose I am making take two substrates, okay, and another one you take non-deuterated version. So, that means you can take CH2 and the CH2. One is the deuterated version, one is the non-deuterated version of 1,7-octadiene. Okay. So, now if you do the alkene metathesis reactions, okay, you charge these two organic compounds with metathesis catalysts. Okay. If you see this one, okay, the first as path B, that is the pairwise, then what are the possibilities? The possibilities are this one and this one. Okay. Now, because these two alkenes will interact, okay, as a pairwise, and these are the two possibilities. So, if it is pairwise mechanism, then you will get the, okay, the hexene, fine, and you will get the other pair, that is the CH2 okay. Now, if you take it as non-pair wise non-pair mechanism, that is the path A, non-pair wise, that is through the metallocyclobutane, okay, then what may be the products total? So, in obviously you will get the cyclohexene, that is this one, okay, then you will get the CD2, okay, that is, and then you will get the CH2, okay, and in additionally you will get the CH2 double bond CD2. So, here you will see you will get additional this one, that is the ethylene, one side CD2 and one side CH2, the deuterated, the mixture, okay, of the ethylene. And if it is a non-pairwise mechanism, that is a Chauvin mechanism through metallocyclobutane, then the statistical distribution of these products will be, this will be 1, this will be 1, and this will be the 2, okay. And experimentally it has been observed that experimentally these statistical distributions are isolated. So, that means the alkene metathesis reactions are happens through the metallocyclobutane intermediate, okay, that is through the non-pair wise mechanism, okay. So, basically the intermediate with the odd number of carbon atoms, okay. So, if you recall, so you will see this odd number of carbon, 3 number of carbon atoms, and in a pairwise there will be 4 number of carbon atoms, okay. So, this is the direct proof that this metathesis reactions happens through the non-pairwise mechanism, fine, okay. It is really interesting, okay. So, now I will discuss about the ring opening metathesis reactions. What are the ring opening metathesis reactions? So, this is the ring opening metathesis reactions. One example, C1 C2, okay. So, let us say like this one, and then basically it will happens through the C1. So, if you take one catalyst, that is the metal-carbene, then what will happen, that this one will be C2 double bond C, okay, and then it will happen the C1 double bond 1 and C2 double bond C. Now, here if you react with C3 double bond C4, now see here, and then there will be another metallocyclobutane ring formation here, C3 C4, and here the M metal. Okay. So, now here you will see, now again it will break, and then what will form? It will C2 double bond C as it is, and then here you will see C1 double bond C4 and M double bond C3. Okay. So, like that one. So, here you will see that this is the cyclic and this is the acyclic. Okay. This is one of the example of the ring opening metathesis reactions, and if we explore this one to a special category of the alkenes, okay, like this one, there were two alkenes group, you can do also polymerization, that is the ring opening metathesis polymerization. So, basically the ROM and ROMP is similar, but here if you have a special monomer, okay, like this one, two alkene groups, you can do the ring opening polymer metathesis polymerization and you can get the hydrocarbon polymer. So, we will discuss in more detail later about the ring opening metathesis polymerization, but this is the basically strategy to make the polymers by the alkene metathesis catalyst. We will discuss later. This is another possible reactions. So, what we have learned? We have learned the ring cross metathesis reaction, ring closing metathesis reaction. We have learned the ring opening metathesis reaction. We also now know ring opening metathesis polymerization reactions. Now, next one you will see, this is called addition metathesis polymerations. So, this is also another polymerization reactions using the using the metathesis catalyst. So, here you will see, if you take a one compound with two terminal alkenes, you will get the corresponding polymers, which is through a addition metathesis polymerization. That we will discuss later about the mechanism, but as you see that there is so many versatile reaction can be done using the single type of catalyst. Okay. And not only that one, it can be extended to the other pi complexes, pi compounds like alkyne. So, here you will see it's very much similar. So, this is alkyne metathesis reactions. So, you can just correlate with the cross metathesis of alkenes. So, here is basically the cross alkyne metathesis reactions. So, you see the exchanging the R1 group here. Okay. So, same metathesis catalyst. Also, you can also do the similar ring closing alkyne metathesis reactions. You can close it, the ring closing alkyne metathesis reactions like that one, and also you can then do the hydrogenation if you want the alkene, and if you need the sp3 carbon center, you can do the further hydrogenation. So, you can make your desired cyclic organic molecules. Okay. Not only that, you can also explore or extend to the other alkene metathesis reactions, like you will see the enine metathesis reaction. So, where one is the alkene, okay, and one is the alkyne. Okay. So, it's basically you will see the alkene metathesis reactions with one alkyne and one alkene, and you will get this kind of compounds from the alkyne. Okay. And not only that, okay, so you can also do the alkyne metathesis polymerization, as you have already learned that the addition metathesis polymerization is very much similar. So, here you will see, if you take, I am just giving a very simple example. So, if you take this bis alkyne benzene, and if you do the metathesis reactions, okay, the suitable catalyst. So, what you will get? You will get okay, and you in return you will get the acetylene. Okay. So, you will see that so many reaction can be done in using the alkyne metathesis catalyst. So, what we have learned that a single catalytic system, okay, system for various metathesis reactions. So, you can assume as a single master key for multiple lock. Okay. And we learned that the metathesis reactions proceeds through metallocyclobutane intermediate, okay, through non pair wise pathway with the odd number of carbon atoms. So, that is a metallocyclobutane will be the odd number of carbon atoms here, like in a 4 membered it is 3 carbon atoms. Okay. So, with this we now very familiar about the different type of metathesis reactions, and this is very important to understand, because when we will go to these are the references, you can read it. Okay. All the very basic whatever we have discussed the very basic metathesis reactions, and all are available in these textbooks. So, why we have read or discussed? Because these reactions, the versatility of the reaction and type of reactions are we are very important to understand. Otherwise, we cannot really explore this carbene metathesis catalyst for the polymerations. And you see that the polymeration is nothing but the extension of the ring opening metathesis reactions. Okay. And also you see that how this reaction proceeds. So, it is very important to understand the mechanism, so that we can choose the right monomer for and the right catalyst for the polymerations if we select the pathway using the metathesis catalysts. Okay. So, in the next class we will be discussing mainly about the metal centers. What are the carbenes? What are the electronic properties of the carbene? What are the bonding and orbital interaction between the carbene and the metal centers? Okay. So, see you in the next class, and till then, bye bye.